Hello everyone, welcome back. In the last lecture, we talked about the idea of a magic wand and how artificial intelligence and machine learning play the role of modern day magic. Now it's time to get practical. Let's explore what's exactly that we're going to build and the technology behind it, and also how all the components work together to form this intelligent wand. So let's start, shall we? So, what are we actually building here? This project focuses on creating a recognition magic wand application using TinyML running on microcontrollers. The idea is to capture motion using an accelerometer and then classify it to specific gestures. For our case, the gestures are called wing, ring, and slope. Every time we perform one of these gestures, the wand should recognize it and respond, either by turning on an LED or by printing a message to the serial monitor. That's our magic spell in action. But what's truly exciting is not just the fun of having a wand, but what it represents. This project teaches us how to take raw sensor data, feed it into a machine learning model, and run it in real time in a tiny microcontroller. The key aspects of what we are building include real-time motion processing, so the wand can analyze acceleration data instantly, machine learning, which is based on classification, which allows it to distinguish gestures from random hand movements, reliable gesture detection by using probability thresholds and multiple confirmations to provide safety from false positives. And finally, efficient implementation on a microcontroller, making the wand low power and always on. So in essence, we're building not just a fun demo, but a real world application of TinyML that can inspire many other projects, from smart wearables to gesture based controls in IoT devices. Now let's talk about the technology that makes this whole thing possible. There are three main components to this. Number one, the accelerometer. Number two, obviously the microcontroller. Number three, the deep learning model. First, the accelerometer. This tiny sensor measures acceleration along three axes, x, y, and z. Think of it as a device that can sense how you move through space, speed, direction, tilt, and swings. For our wand, the accelerometer is the eyes and ears, which captures every flick and wave of your hand. Second, the microcontroller. For this project, we use the Arduino Nano 33 BLE Sense, which is a compact yet powerful board with a built-in 3-axis accelerometer. This makes it perfect for gesture recognition because we don't need any external sensor modules. And finally, the deep learning model. This is where the magic of AI comes in. The model has been trained on accelerometer data to recognize our three gestures: wing, ring, and slope. Whenever you move the wand, the raw accelerometer signals are passed through this model and it outputs which gesture it thinks you have performed. Now these three pieces, sensor, microcontroller, and model, come together to form the complete system. Now let's walk through the actual workflow of this application step by step. So number one is input capture. The accelerometer captures raw acceleration values along x, y, and z axes. For this project, data is sampled 25 times per second, which is a sampling rate of 25 Hz. Number two, the inference. These three values, which are captured by the accelerometer, represents motion in three directions and are directly fed into the machine learning model. No heavy pre-processing is required, which keeps the system lightweight and efficient. Number three, the processing and output. The model then checks whether the captured motion matches one of the trained gestures. If yes, the wand responds. The response could either be an LED turning on or a message being printed on the terminal. That's the high-level workflow, from capturing the movement to giving real-time feedback. Gesture detection model review. So now let's take a closer look to the model itself. The model used here is a convolutional neural network or CNN, and it's surprisingly small, just about 20 kilobytes in size. That's smaller than most images you download on your phone. Yet it's powerful enough to classify gestures in real time. Here's how it works. The input of the model is raw accelerometer data, 128 sets of x, y, and z values. Since we capture data at 25 Hz, this corresponds to about 5 seconds of motion. Each value is a floating point number representing acceleration in one direction. The output of the model is a set of 4 probability scores. These scores represent the likelihood of each gesture: wind, ring, slope, or no gesture. All the probabilities add up to 1, and the gesture with the highest probability is considered the output. To reduce the errors, we usually require the probability to be above 0.8, which means the model is at least 80% confident before confirming a gesture. This is small but efficient CNN is the core of the intelligence inside our world. Now let's break down the entire application into its key software components. So first is the main loop. Our application runs in a continuous loop. Since its model is small and simple, there is no pre-processing required. We'll be able to run multiple interference or inferences per second. Then comes the accelerometer handler. This part captures raw motion data from the accelerometer and writes it to the model's input tensor. It also manages buffering, since we need 128 sets of values before inference can happen. For the Arduino Nano 33 BLE sense, downsampling is applied because its accelerometer runs at 119 Hz, while our model expects 25 Hz. TensorFlow Lite Interpreter. This is the engine that runs our ML model. It takes the input tensor, applies the CNN model, and produces the probability outputs. Gesture Predictor. This component interprets the model's outputs and decides whether a valid gesture has been detected. It prevents false positives by requiring consecutive confirmations. For example, if the board requires 15 confirmations for wing, 12 for ring, and 10 for slope, these thresholds can be tuned depending on the hardware and software performance. Output handler. This is the final stage. Based on the detected gesture, it lights up an LED or prints a message to the serial port. It provides immediate feedback so the user knows the gesture has been recognized. So the system works as a pipeline. First comes the data capture, then it is followed by the model inference, then comes the gesture prediction, and finally the user feedback. So here is the components that we are using in a simplified block diagram. So as you can see, the accelerometer, TF-Lite interpreter, gesture predictor, and the model, and also the output handler is shown here. So moving next, before deploying the wand in real life, we need to ensure it works correctly. This is where testing comes in. The GitHub repository provides test files. First comes the Magic Wand test.cc. It runs interference on sample accelerometer data to verify model's accuracy. Then the accelerometer handler test.cc demonstrates how to read real-time data from accelerometer. Then gesture predictor test.cc analyzes the motion of the model's outputs and checks the effectiveness of gesture detection. By running these tests, we can identify issues early, whether in data acquisition, model inference, or gesture prediction. This ensures the wand works reliably once deployed. Finally, let's look at the basic flow of the Magic Wand application as a whole. First step is the data capture, the accelerometer which continuously collects raw motion data. Then comes the memory allocation. The data is stored in a buffer waiting for enough samples. Then comes the model inference. Once the buffer is full, the CNN model runs on the data Number 4. Gesture detection. The output is checked against thresholds. If a valid gesture is found, then it is confirmed. Then event triggering. Finally, the wand performs an action like turning on an LED or sending a serial output. This loop repeats continuously, allowing the wand to remain always on and responsive to every gesture. So, to wrap up this section, we have seen how the Magic Wand project is designed, the technology behind it, and the workflow of data capture and inference, and also the individual components that make it function. You can now see the complete picture. A sensor captures motion, then a deep learning model interprets it, and the system provides real-time feedback. In the next part of the course, we will be moving to even deeper parts like the accelerometer handler, gesture predictor, and the output handler. We'll also discuss how these modules are optimized to work on resource-constrained microcontrollers like Arduino Nano 33 BLE Sense. This marks the transition from high-level design to low-level implementation, where the real fun begins. So, let's go. Thank you.